Hello everyone. Today we are going to talk about relativistic photonics regarding taking into the boundary condition inside consideration and talk about the power transfer. And at the last one, we will use a simple particle extracted from the layer of the electron beam and try to analyze how the Poynting vector and the power flow, how the EM wave and the space charge wave interact with each other. The first section is about the dispersion growth rate. Here, taking the boundary condition as we discussed before into consideration, insert into this picture where the blue region corresponds to the vacuum between the intersection between the vacuum and electron beam, and the red one is the dielectric with the vacuum. And with this boundary condition, we can get a linear algebraic equations shown here, where the A, D1, D2, and C correspond to the dielectric vacuum EB region that we have obtained last week, where the EP is the equivalent relative permittivity of this relativistic electron beam. So it's relativistic, so we have a gamma here. And with some relation here, we can get the dispersion relation for both coupled EM wave and the space charge wave. So if we do some specific values, we can find just the EM wave without the coupling of the space charge wave, and also just the space charge wave without no dielectric layer inside here. So to consider no electron beam, we of course the plasma frequency goes to 0, and with no dielectric, of course A is just equal to 0, which means there's no dielectric here, and epsilon r equals to 1. So first we would like to discuss just the EM wave. With this condition, we can simplify into this form, and to just plot the picture to visualize this result shown here, we can see that the dispersion curve, just in this picture, we just plot two lowest mode, which is TM0 and TM1. They are all inside a region created by the cutoff line and also the asymptotic line, where the velocity corresponds to C, and C divided by refractive index. Here we have an extra line which corresponds to a drift velocity, and later we'll discuss that what's the importance of this line to be inside this region. And to visualize the field inside the layers, we can see the right hand side here, where we have the TN0 and TN1. And here, because we consider no electron beam, so of course B equals to A, so therefore we only have A term here. And for y larger than A is the exponential decay term, and here inside a sinusoidal wave with different modes. And for the next one, it's the space charge wave, which is no dielectric. So in this visualized field, we can see that there's no A, there's just B here because A equals to 0. And epsilon r equals to 1 because no dielectric, so relative permittivity equals to 1. And it degrades to this form, where it corresponds to this picture. And you can see that they're both bounded by this, by the two curves with the same slope with V0, which is drift velocity of the electron, with some different offsets. So, but the real case is that consider where the electron beam is really small, but it's not equal to 0, so therefore the plasma frequency is just much smaller than omega but not equal to 0. It will be actually in this form, where it is actually just like where omega plasma frequency equal to 0, which we have just discussed before, where there's no electron beam. inside the discussion. And so we can just borrow the picture from this to try to get some concepts right here. So without plasma frequency, the curve is like this. But when taking curve into consideration, the actual omega, the actual frequency in the K is not in this point, but rather the orange point here. And here we start to notice the importance of this line with slope of drift velocity, because that if the drift velocity is not inside this region but rather outside the region, which means that the drift velocity is smaller than the phase velocity of the EM wave, that means that Cherenkov radiation is not occurs, and also means that the electron beam is unable to provide energy towards the EM wave and thus grow the EM wave. So in the later on section, we all have a really important knowledge that we should have a velocity in larger than phase velocity to enable the further discussion. So here we consider that if the plasma frequency equal to 0, is equal to kz, and we have a consider delta kz, which is the small deviation from the from this point, but with same frequency here, and we can plug this kz into this term, then we can get the corresponding solution to be like here, where the hy0 is actually kz0 divided by Lorentz vector. And after some mathematical tools where this can be shown in my questions that I have answered, we can get there's 3 solutions for delta k, which means that there's 3 k for the solution, and that's why we can see that here I plot 3 orange points rather than other numbers. So here we can see that it allows 3 values for the wave vector correspond to 1 frequency, and this is quite trivial because that for n larger than 2, it actually just back to 0 because of the periodicity of this exponential complex form. So with this, what we just obtained, we can first consider the case where n equals to 0. And we can see that it actually corresponds just to the growing wave because the wave is proportional to exponential minus ikz. And specifically, the growth rate is expressed in alpha with this form. And we can see that there's an exponential decay inside the growth rate, which can be characterized by E minus A, which is the layer of the vacuum. We can also consider it as the distance between the EM wave and the electron beam. The larger this distance is, the smaller the growth rate is, and this is understandable because the longer the distance, the lower the interaction between them. And to consider the interaction between the electron beam and the dielectric, we first need to notice that the actual thing that interacts with the dielectric, with the EM wave, is not the whole electron beam, but just the surface of the electron beam. So therefore, we can consider that we don't need to consider an infinite thin electron beam, but rather a thick electron beam, but with decay to a certain degree, acceptable degree. And that degree we call it the skin depth. And the skin depth is defined as when the field just decays to exponential minus 1 as the conventional value of it. So we can record the field expression of the electron beam in this form, and we can see that the skin depth just corresponds to ky times y equals to 1, and it approximates to hy times delta. And consider the case that we just typically discussed, where omega frequency equal to omega 0 and kz equal to T0, we can get the results that the skin depth in this term. And it looks the importance of this one is the gamma term here, because that this if the gamma is equals to 1, then of course it's kind of hard to achieve a probable interaction in order to grow the electron in order to grow the EM wave. But if we have a relativistic electron beam, then this gamma is very large, and thus we can easily couple the EM wave from the electron beam to amplify our signal. So to further visualize this picture, of course, at first we discussed the case here, and now we consider the actual picture of this. So the growth rate, it corresponds to the dashed line of it, and we have a maximum at point A, which corresponds to m equals 0 and 2, and for m equals to 1, it corresponds to the green dots here. So it actually borrows a picture where plasma frequency equals 0. It's inside here, where we are not at a red point, but just with a delta kz offset from it. So a numerical example can be shown from here. So as the dashed line goes, we can see that it started to grow and have a maximum growth rate at point A, and thus slightly decays afterwards. So next, we would like to talk about the power transfer between the electron beam and the electron in the EM wave. So consider the power of the EM wave to be this form, and the power of electron beam to be this form. And where the initial condition, or rather the starting point, corresponds P0 and 0. It may sound weird to be 0 here, but it is kind of intuitive afterwards, because that negative power will correspond to a positive power of the EM wave. So that's what. So, and also we can, by simple verification of just do the derivation and plus them together, we can find that this definition actually corresponds to the energy conservation of it. So here is the initial setup. But to further doing analysis, here we have a important assumption that we would like to address, is that we consider a stepwise difference between each segment when we consider the power transfer, so that the V0, the true velocity of the electron beam, rather can be considered also as kinetic energy of the electron beam, is not just grow continuously, but we consider a discrete, stepwise, rather decrease and stepwise increase of the electromagnetic wave. So with this concept, of course, we can divide it into several segments. And for the nth segment of the EM wave, we can consider that it's have two constant an and alpha n, where the first segment, of course, corresponds to P0, as we have just defined here. And to give the growth rate of the EM wave, of course, comes from the kinetic energy of the electron beam. So therefore, we consider the kinetic energy of the electron is expressed in this term as what we have, as we're familiar, and is defined in the average beam velocity of it. So to get the power per unit width of the electron beam, so B means the electron beam here, but not the P here. This P is corresponding to the power of electron EM wave, and this P sub B is the electron beam. Is the total power of the per unit of the electron beam, of course, just times the number density of it. The number density can be get from n times v times delta effective, where the n is the average number density per volume, and v is the velocity, and this is delta is the effective beam thickness. And this is actually equals to the effective beam thickness. It actually equals to the skin depth delta that we just defined before. If the beam is thick, and if the electron beam is actually infinite thin, then this delta corresponds to the actual width of the electron beam. And here is just a simple verification just by the unit. Now we can see that this is actually the power per unit. So from the energy conservation that we just verified before, we can get the power difference between each segment, the condition of it. And of course, the decrease in kinetic energy corresponds to an increase in EM wave. So first, we can calculate the decrease in kinetic energy of the electron beam is, of course, the n plus 1 segment minus the n segment. And this is actually just the plus minus sign. So, of course, the increase in the EM wave plus the decrease of the EM beam, electron beam goes to 0. And from this relationship, we can get the normalized drift velocity for the n plus 1 segment, where gamma n plus 1 is expressed in here. So to vividly show the results, we can have some plots. So of course the goal is to grow the EM wave. So therefore, along the z direction, we can see that the power growth along the EM wave. But the power growth doesn't grow infinity. It stops at some point. And this point corresponds to the growth rate goes to 0. And when the growth rate goes to 0, we can see that the normalized drift velocity also goes to a constant value of it. And this can be considered that in order for the electron beam to provide energy for the EM wave, the drift velocity, of course, needs to be larger than the phase velocity of the electron beam. So at a certain level, it was when the electron beam drift velocity of the electron beam is not large enough, then it will stop growing, and thus the power will fix to a specific level. But if the drift velocity doesn't increase, that doesn't decrease, and it's as the orange line here, where we say that the beta is a constant term of here. But it is not practical. A more practical way to do this is that rather than trying to keep the drift velocity at a constant, we can try to slower the phase velocity of the EM wave down across the amplification region. And this can be done by just tuning the epsilon r, or rather the refractive index of the medium, dielectric medium, in order to slow down the phase velocity and to keep the drift velocity higher enough, and thus the electron beam can keep providing energy to the EM wave via its kinetic energy. So today's next section is a single particle approach, and as its name suggests, we use a single particle, which is a single electron, to analyze. And here is the picture that quite similar before, but a layer of a dielectric and an electron beam distribution here. So what we do is that we extract an electron from here toward the x direction, so it's go inside the paper this direction. And the kinetic energy of an electron, of course, is obtained in this term, and do a time derivative, it's correspond to this term and the Lorentz vector that we are familiar before along z direction, because we assume the electron goes at z direction. And the corresponding equation of motion along z direction is expressed in this term, where we have discussed in the previous section, where we have a gamma to the power 3 in the denominator. So we consider the electric field in this form. Then we can plug this back to the equation of motion in order to get the relationship of the velocity, where the big omega is the effective measured frequency at the position of electron. So it's omega minus v0 times kz. And recall that before we usually have an omega prime, which is the frequency at the restaurant of the electron. That needs to be times an extra term gamma. So with the relationship of the velocity, of course we can get the velocity along z direction over the time, which is as shown here. And to integrate over the velocity gives the position, where the z position right here, and therefore we get the field, the electric field, expressed in this term. And we can just plug what we obtained, the electric field along z direction, into the kinetic energy derivative, time derivative. Then we can get this relationship. And from this relationship, we can start to get the average, try to get the average kinetic energy. And first, we would like to average over the phase between the electron and the electron beam and the EM wave, and with the assumption that big omega is much smaller than the omega term, where the big omega is the observed frequency measured at. And therefore, by integrating over the phi term here, we can get this result, and further duly integrate over certain time, where the time is divided by v drift velocity times the time here, when we can get the average kinetic energy, the delta average kinetic energy of it. And here we have a function g with parameter big omega tau, and the tau is what we define as time here, which is L divided by the drift velocity over a certain distance L. So looking into a graph of the small g function, we can see that this is actually just a gain function, because this is just proportional to it. So when this gain function is larger than is a positive, then it means that the electron beam gains energy, and therefore the EM wave lost the energy and has a damped wave. And when the gain function is smaller than 0, then it's actually amplification of the EM wave, and thus we can get a growing electron beam, EM wave rather. And the condition here can also be considered that, as I just mentioned before, the Cherenkov condition, where the drift velocity, of course, needs to be larger than the phase velocity of the EM wave. So now, with this, then the next step is we are trying to find the specific expression for the power gain of the EM wave along this the z direction of the dielectric coating. So first we need to obtain a field component that we have just learned before at the dielectric, and also for outside the dielectric region, where the blue region is expressed in this form. And the relationship between the A coefficient and the C coefficient is expressed in here, which is obtained at the boundary condition y equals to A, which is exactly here. And the corresponding Py and Hy is discussed previously, and of course the ky is what we said that maybe alpha y would be a better way for us to understand. So to get the power per unit length along x, where it's the out of going inside of the paper, so I denote in the green and the orange cross with circle here, it's actually do the pointing vector or pointing vector and times the y dy. So therefore we get this expression. And also to compare the EM wave power with the kinetic energy, the relationship is defined here, where the I is not the intensity, but the current. And of course we know the current is equals to the number of electron per volume times the electron and times the area, also times the drip velocity. And therefore divided by the electron is actually just the average number of electrons per second. So therefore this means that we can successfully transfer energy towards the power because we have a per second unit difference here. And if we consider the longitudinal electric field E0 at y equals to b, then we get this expression, and combined with the p that we just obtained here, we can get the second equation here, where the f is actually defined here, and this is actually the similar component we just obtained here with just a simple swapping of it. And therefore now we get the p, and also we have the delta p relationship with the kinetic energy. So therefore we can obtain the gain of the EM wave, and this is our ultimate goal. So with a small gain function that we just showed in previous slide, where the actual plot is plotted in this way, and this is the case where for the lowest mode, which is Tn0. And please note that the kz here is not an arbitrary number. The kz here must be the value that corresponds to the dispersion relationship, which is what we just mentioned here, where we just found that delta k has 3 possible solutions because it's on the exponential due to the periodicity of the complex exponential, where we have m equal to 0 and 2 at the A point, and n equals to 1 at the B point, and A is the largest gain of it. So that's it. So today we discussed, first we introduced the boundary condition, and then we try to find a power transfer from the electron beam to the EM wave. And as section, we use the single particle approach, which is extract just a single particle, which is electron from the layer along the x direction, then to find the kinetic energy, find it, and plug in the exact field expression we obtained before to get the power, and try to connect the kinetic energy and the power to get the delta P, and at last get the gain of it. And here are my questions. So previously, before, we have mentioned a point where this condition can be obtained, and we can just I just show the simple derivation of it, that we just do the chain rule, and we will find that they are all negative, and all negative value plus together would be, of course, smaller than 0. So that's it for today. And if there's any mistakes in my video, please tell me, and I will fix it as soon as possible. Thank you for listening.